In addition to a time axis running this way, we live out here at the present day, and there's a distance axis going the other way. That is exactly the point of the first several slides, so I'll get to that. So this model started coming together almost 100 years ago with Hubble's famous measurement. Sorry for the jump from dark to bright. Everyone's eyes should hurt. Measurement of the recessional velocity of galaxies versus the distance to those galaxies, the proper distance. And he noticed that, lo and behold, basically everything outside our local group is flying away from us. And the farther away from us, the faster it's receding from us. This, thankfully, was not long after the invention of general relativity. And people reasonably quickly realized that this could, rather than us being the least popular point in the universe, be due to space expanding. And the more space there is between two things, the faster they get farther apart. So this actually, this was simultaneously discovered by a few people, including a Belgian priest, Georges Lemaitre, who might shortly be renamed the Hubble-Lemaitre law, pending a resolution at the IAU. So to understand this, you basically have to take general relativity and solve for what happens in a universe. That gets complicated if you allow all possible universes. If you try to do the general relativistic effects of everyone in this room interacting on everyone else in the room, it effectively is, well, complicated to do, and also very small. But to simplify life, we make one major assumption, which is to invoke the cosmological principle. We say that the universe is homogeneous and isotropic. Homogeneous in the sense that space is basically another point, and isotropic in the sense that any direction you look, you'll see essentially the other direction, statistically. This is sort of equivalent to saying that we're not special. We don't happen to be at some fancy spot in the universe looking in a direction. We're as good as any other observer anywhere else in the universe. We don't have a privileged view. And the nice thing is, once you invoke these, once you require these and plug them back into GR, thankfully, that one's actually very close to 0 experimentally, so we can more or less ignore it for the purposes of the present talk. When you take this metric and plug it into Einstein's field equations, you get a relation between essentially scale factor and whatever stuff you choose to include, whatever fluids you throw into the universe to operate as, say, matter, radiation, dark matter. If you're reading ahead in the textbook, dark energy. Whatever stuff you want to include, GR dumps that out in a form called the Friedmann equations, because Friedmann was the first one to sort of plug everything in and work out the simplified form of how the scale factor relates to the stuff in the universe. And that's because the curvature is essentially 0, and the scale factor is basically the last unknown in this. At some level, all of cosmology reduces to trying to measure this scale factor, which, excellent question, how do we measure it? That's the point of the entire field. For decades, cosmology was referred to as a search for two numbers, primarily the Hubble expansion rate, so the slope of this line, which it turns out is the first derivative of the scale factor, and what they called at the time the deceleration rate of the universe, how fast it was decelerating, so the second derivative of the scale factor. So essentially, people were just Taylor expanding the scale factor into a constant value, which we set to 1 today, a first derivative, the Hubble expansion, and a second derivative, the deceleration. And then an unfortunate thing happened. Well, fortunate for some people. People went out and measured these things. They measured the distances to supernovae, how bright it is, compare that to some known intrinsic luminosity, and you get a luminosity distance. You then measure a redshift associated with that, and you plot up Well, something like the distance or a proxy for the distance, in this case, it's distance modulus, as a function of redshift, and you get a relation between the two. And depending on how your scale factor evolves over time, that relation will change. Now, the unfortunate thing is that this showed that the deceleration parameter, negative the second derivative, was negative. That the universe was not decelerating, that every textbook had been wasting lots of minuses everywhere, and that, in fact, the second derivative was positive, that the acceleration, the expansion rate is increasing. So this was the discovery of the accelerating universe, that the expansion of space did what I mentioned earlier. It slowed down for a long time, and then it started speeding up, which is a particularly odd thing to do, unless you start invoking other physics. So you can take the Friedmann equations, which again relate the scale factor to the material that you put in the universe, the stuff that you put in the universe, and you can plot up, say, this is a plot of how that stuff evolves versus time. So here I have the scale factor, or equivalently, the redshift. Redshift scale factor, we use them in 1 over 1 is 1 plus the other, versus the energy density in a thing. Matter and radiation both decrease in energy density with the scale factor. This is easy to understand. If you have particles in a box and you double the linear dimension of that box without adding any new particles, the density is down by a factor of 8. Right? The matter density redshifts as the cube of the scale factor. So the matter density drops off with scale factor. The radiation density drops off, but it also, all your photons stretch out. They lose an extra factor of the scale factor. So it redshifts as scale factor to the 4th. So radiation and matter drop off. And if you take these two terms and you plug them into Einstein's field equation, plug in your metric, you get something that does not in any way accelerate. It decelerates, which is why everyone said it decelerated. The thing that you need is one of these flat terms, something that doesn't dilute as you expand the. The only way to reconcile the observations of supernova luminosity distances with the measurement of the redshift is to include some other term that starts to peak up and becomes more significant than radiation and matter. This is not exactly flat. It's not saying that as you expand space, it stays the exact same energy density. This error bar is sort of a representative uncertainty. The actual error bars are about 1/4 that large. It's extremely well measured today what its density must be. But as you extend farther and farther backward and forward in time, we're a little unsure. This is the thing that we call dark energy. Dark because it doesn't couple to the electromagnetic field. It has no EM. It doesn't interact with light. So it's dark, same as dark matter. Dark matter is just matter that doesn't interact electromagnetically. And energy because it's an energy density. That's essentially what we know about it. That and the fact that it seems to have a fairly constant energy density. We parameterize this by an equation of state, W, that relates its pressure to its density. We don't know if that's constant, if it changes over time, or if even the equation of state changes over time. One of the big mysteries in cosmology, one of the big missions, is to measure this equation of state and measure its time evolution. The reason this is important is because if you just look at today, at redshift 0, at scale factor 1, something like 70% of the universe, the energy density of the universe is in this dark energy term. You know, radiation is negligible, matter is a small portion, and most of that is dark matter. And as you go forward, you can see the dark energy becomes more and more and more and more and more significant. All of the stuff that we're familiar with becomes less important. So this is a huge piece of our pie that we don't understand. Well, we understand the first thing about it. We don't understand the second thing, I guess. We're really trying to get a handle on this. The other thing worth saying from this chart is that all of this knowledge comes from essentially 2 points in the universe's history. It comes from measuring stuff locally out to about redshift 1, so down here, where it looks like, and from measuring stuff out at redshift 1000, from looking at the cosmic microwave background. And the universe looked very different at the 2 times. Right? Out here, you can see the radiation. You cannot see the dark energy. Out here, you can see the dark energy. The radiation, well, we can measure exactly because we have radiometers. To make things worse, people have also proposed more complicated forms of dark energy. It may have sort of tracing forms. They may have all sorts of complicated time evolution. We aren't sure. For the moment, the goal is really to nail down what its energy density is. It evolves over time. So to do that, ideally, you would want something like this. This is a theoretical plot of the scale factor as a function of time for the entire history of the universe. It would be great if we had lots of measurements all along here showing that this matched. Again, this is mostly measured here. So we've got two measurements here. All of this is inferred from what we've measured. It's pretty concrete down to sort of past inflation or into inflation. It starts to get a little hand-wavy. But what we really want to do is try to measure this scale factor. If we know the scale factor is a function of time, we can infer what the fluids must be as a function of time, equations of state must be, what all the things happening are. It's like when you measure the radial velocities of orbiting stars and you infer what their masses are, right? We know what the rules are. If you tell me some of the components, then I can extract the other ones, solving a determined system. So the goal in any study of, well, dark energy is to try and make one of these, measure the scale factor as a function of time. Now that's a tricky thing to do because fundamentally what you're trying to do is measure the underlying metric, right? You want to know how big is, how big space is. And the thing is, if space expands, so does whatever you're using to measure space. Photons expand, time dilates, all sorts of difficult things get in the way. Historically, people have done it with these luminosity distances, with standard candles, supernovae going off in galaxies. Luminosity distances to them so that you can then expansion history. The other option for directly measuring the metric is to use a ruler. If someone had helpfully scattered yardsticks throughout the universe, extending back to the early universe, then we could just look at those and see what angular diameter distance they covered. Thankfully, the universe did that. It's a happy coincidence of cosmology that the universe is completely covered in standard rulers. For a long time, people tried to use galaxies as roughly standard rulers. We can do much better than that. And to see how, we have to go back to another picture of the universe's history. So this is, again, time runs from over here this way. We live out here somewhere. This is that early plasma era. This is that boring period where nothing's happening. This is the boring period where structures are forming. You can tell I'm biased towards the plasma. It seems more. In the plasma, this is what we call the primordial plasma of the universe. Again, lasted sort of 380,000 years. The seeds for all the structures that formed later must have already existed. If the universe were perfectly uniform and there were no slight overdensities, slight underdensities, you would never have gravitational collapse onto those seeds. You would never have structures popping up, galaxies, people, everything. And we know that those things do exist because I'm a lot more dense than the average part of the universe, right? There is an overdensity that gravitationally collapsed eventually. Those must have been seeded very early on. The current models have them being seeded organically during inflation. The details of exactly where they came from don't matter that much. The important thing is that they came from early on. And that means at time 1 second, there were already chunks of the universe that were a little bit more dense and a little bit less dense than other chunks of the universe, which means they had slightly higher pressure, slightly lower pressure. And the thing about a region of slightly higher pressure in a plasma is that when time runs, it emits a pressure wave. Pressures propagate. So this is what's known as the baryon acoustic oscillations. It's unfortunate that it's called baryon acoustic oscillations because it was a baryon photon plasma that was acoustically oscillating, these pressure waves propagating through. So the idea is that early on you had some random background of fluctuations, overdense, underdense, whichever way. At the start of time, each one of them pushes out a pressure wave, and that pressure wave carries on through the plasma. And it travels through the plasma while the whole thing is expanding and cooling off until the plasma stops being a plasma, until it cools off enough that, again, it goes neutral. The photons and electrons bind together. At which point, the photons that are driving that pressure wave leak out. They all fly off, and we see them as the CMB 14 billion years later. And the pressure wave essentially stalls. So what I'm going to show here is a movie. So this is an overdensity. And it will show in 3 different colors: the cold dark matter, the baryonic matter, and the photons. So the photons are going to push the regular matter, the baryonic matter. until decoupling, at which time the photons will run away. The cold dark matter doesn't care about the light. It doesn't care about this photon. You have this lump of dark matter, lump of baryonic matter, and they'll slowly gravitationally attract each other until they pushing out, the photons run away, and now regular matter falls into the matter, and dark matter falls into the regular matter. And this is what that perturbation looks like many billions of years later. So again, we started with a point, and anywhere you have a point in the universe this happens, we're all well into the linear regime, so you don't have to worry about interactions with each other. Every point of overdensity or underdensity gets replaced with, well, a central feature and a shell. And that shell is a particular distance away. It's however far that pressure wave could travel. And we know how fast pressure travels in a plasma. We know how long it had to travel. We know how the universe was expanding. We can calculate from first principles how far it would go, how large that shell is. And then the thing is, things can only move at standard pressure sound wave speeds. Once you know all the things, so really what we do, we have a model with 5 free parameters, and you fit it to cosmic microwave background measurements. When you're looking at the CMB, you're getting a direct view of the photons as they exited. You get a direct measure of the sound horizon at decoupling from the CMB. So it is a fit. If you knew all the material, all the components, then you can do it. Right, so this is essentially frozen because the speed of sound in the later universe is quite small. And today, when you look around at galaxies, you see essentially this. If you take all of the mass in the universe and you check how far it is from all other mass, it likes to be close to other mass, and it likes to be 150 co-moving megaparsecs away. Say 150 megaparsecs today. When the universe was, say, at redshift 2, so a third the current size, it was a third that far away. It was 50 megaparsecs away. So these things are frozen in. And if you go and you look at galaxies, people have done this many times. You can measure the correlation between galaxies, just measure the distance between any pair of galaxies, histogram it all up, and lo and behold, you get this beautiful bump at 150 co-moving megaparsecs, or here they've divided it by h inverse. So it looks like it's sort of 100. But this is a structure that exists in the present-day universe. It's a structure that we've measured out at the cosmic microwave background. And you can use this just like you're using the standard candles to measure luminosity distances to things. You can use this separation between matter as a standard ruler to measure the angular diameter distance between things. This is what that sort of a plot looks like. This is something like the co-moving distance to a redshift versus redshift. Those 4 points that I showed on the previous slide are marked here. Way out, if you went to redshift 1100, you would see a point from the CMB. This gray error bar is the current allowed uncertainty on it. This works beautifully. The thing is, to try and understand dark energy, really this chunk that you want. Fill that in. And the reason is that, well, early in the universe's history, past, say, redshift 2, 3, somewhere around there, dark energy is fairly insignificant. Matter and radiation still dominate over it. It's less important. Later in the universe's history, so closer to us now, there's just a smaller chunk of the universe that you can see. You don't have access to enough of these BAO scales to get a good measurement of the scale factor very close in. So it's really a chunk past redshift 0.8 to about redshift 2.5 that you want to nail. So how would you do that? This is currently our best handle on trying to measure dark energy, is by trying to measure scale factor over this big. Well, historically, people have done it with galaxy surveys. This is great. It works. I showed you 4 examples of it working. Fantastic. The problem is it's very hard. It's very expensive. And it gets extremely hard past about redshift 1, because these have to be spectroscopic measurements. This is a plot of just distance to galaxy versus angular for several tens of millions, if not 100 million galaxies from SDSS, Sloan Digital Sky Survey, sort of the canonical. And you can see the large-scale structure of the universe. It really doesn't work past redshift 1 because all of the good emission lines redshift into the atmosphere. It's hard to see things, get good spectroscopic measurements on things past redshift 1. The other thing that's funny about this is that the scale we're interested in is roughly something like I've drawn here. Resolving every individual galaxy here is a lot of work to determine that big scale. I have a colleague who describes this like trying to make out footprints on a beach. If you wanted to tell if there were footprints on a beach, you could go measure the exact three-dimensional position of every grain of sand on the beach, reconstruct the presence of footprints or not, or you could squint a little bit and defocus your eyes and see beautiful footprints. So the idea is the same here. You do not need to know where every one of these galaxies is. That is not helpful information. You could blur the whole thing out and see it just as well. The scales of interest are fine, which actually opens up a whole new world. You don't need to resolve individual galaxies. You can see bulk emission from galaxies, what is now called intensity mapping. Map the bulk emission from, say, a cluster, which means that you don't have to use optical light anymore. In fact, you're better off using hard to use optical because all the lines sort of smear together. Instead, what's proposed is using 21 centimeter, the hyperfine transition of hydrogen. It's a nice isolated line. It's alone. Hydrogen is everywhere. You can essentially just map out spectroscopically where all the material is. It just so happens that redshift 0.8 to 2.5 is also a relatively clean radio window. Particularly when we started this project, analog TV had just turned on, and digital TV hadn't turned back on. So all of the people that were polluting stopped polluting one day. So all the spotlights turned off, and it was just clear. Makes a fairly good band. There's some problems with it, though. If you try to design an instrument to do this, you're driven by the farthest away things. They're the faintest. They're the smallest. You have the worst resolution there. All sorts of things work against you at the high redshift end. And you find out that you need a telescope that's about 80 meters, not just for resolving power, but 80 meters collecting area. To be a filled 80-meter aperture. Which, OK, we can do that. We can make 80-meter telescopes. It's been done before in radio. Not bad. The bigger problem, though, is sort of threefold. Remember, the universe reionized with those first stars. So to first order, there is no neutral hydrogen. The 21 centimeter transition is a forbidden transition. The mean lifetime is 10 million years between spin flips. The hydrogen that isn't there doesn't like to emit in this band. And it's so far away that you effectively can't see it. So at some level, you're looking for something that doesn't exist, can't happen, and is too far away to see anyway. Which means you can't just build one 80-meter dish. You'd need about 1,000 of them. You need an enormous light bucket. You need lots and lots of pixels, and you need a long integration. So, like I said, we can build big dishes. We can apply for a millennium on one of these. No one will give it to you. And the problem is these are, one, expensive, but two, sometimes they fall over. Megastructures are slightly built to build. It's just complex. This was rebuilt, and it's better now. It's a better telescope, so not too bad for that one. One thing that some people proposed, a group out of the UK called Bingo, was building a focal plane array. So this is how optical telescopes work. You don't just have one pixel at the center of your dish. That would be a terrible way of taking pictures. Megapixels or gigapixels. In radio, that's harder because we're not dealing with, several hundred nanometer wavelength light. We're dealing with meter wavelength light, which means you need a much bigger focal plane. And when people tried to benchmark this out, these Bingo people at lower redshift, so the easier version of this, needed 50 feeds that were each 2 meters wide, 7 meters long, and hanging 75 meters off the edge over a dish. So scale that all up by a factor of 4, and you get to something like what we needed. It doesn't obviously work. In fact, it effectively prohibits. So the next option is maybe an interferometer. You can radio. People have been using interferometer for ages. Works out great. So just to remind people the way a traditional telescope works, hopefully people are aware of this. Light comes in, focuses to focus. Essentially, what's happening here is that the light comes in, and it's all traveling the same path length if it comes from here, and it appears constructively at this point. If it's coming in from some other angle, it travels a slightly different path length different portions of it travel different path lengths to here. Instead, they focus constructively over here somewhere. Where it focuses constructively is where you get your image. You don't have to do, essentially, a mirror is a big interferometer, right? It is doing interferometry. It's doing adding interferometry, but that's how optics work. The way that radio antennas tend to do it is not adding. We do it with correlation interferometry, where you take a bunch of dishes, you stick them out in a field, you measure the electromagnetic wave coming in, but instead of taking it in analog and shining them onto the same surface and looking for an interference pattern, you measure them both digitally, throw them into a machine later, just a big supercomputer, and slide them past each other and check what the delay is, how much signal they have in common from different delays, which correspond to different directions on the sky. It works great. I had 2 dishes like this. Essentially, I end up with 2 pixels on the sky, each with twice the collecting area of one of these dishes. You've doubled the collecting area for each one. If you have 100 of them, you have 100 pixels on the sky, each with 100 times the collecting area. It's a very efficient way of doing things, not just for resolution. You can spread these out and get higher resolution, but also for sensitivity. The problem is that you have to do it pairwise. You do A with B, A with C, A with B, B with D, C with D. It gets expensive quickly. It scales quadratically. And when you get into the thousands, it becomes impractical. Into the millions, it's still beyond the reach of any supercomputer. So when we started this, 1,000 couldn't be done on even the largest supercomputer on the planet. So we said, OK, that doesn't quite work. Back to the drawing board. This is a traditional telescope. How about we do this as a phased array? So a phased array works differently from a normal telescope. It does essentially the same thing. You take all the light that hits the surface, and you interfere it additively. But you do it on your own. You don't build a mirror. You just put a bunch of detectors there. Measure the signal at each one, delay each one through a cable, add them all up. It's the same if I had focused them onto a point. Then you realize, well, why did I build the mirror? Return that to Home Depot or wherever you got it. Just cover the ground with these detectors. You do the same thing. This still acts like that original mirror. As long as these are spaced the right amount, it is physically identical. Mathematically, it behaves exactly the same way. That saves you a lot of money, potentially. And it lets you do other things. If I can take each of these and digitize them separately, not add them up in cables, but add them up in a computer, then I can add extra delays in the computer. I can shift my data around, and I can point it. Add a little bit of extra cable over here. Makes it look somewhere else. And then I realize, hang on, I returned that big dish. I've got a giant pile of cash. Let me go buy more computers. Instead of doing it once, you do it many times. You take the same data, and you interfere it additively one way, another way, another way, another way, another way. And you can look independently in as many different directions as you have detectors on the ground. This is great, because it turns out that computers are cheaper than steel. And every year, silicon gets cheaper and more expensive. So as a general rule, anytime you can throw out a dish and get a circuit board instead, it's a win. This is much, much faster than a single dish. If you have 1,000 of these detectors, it's 1,000 times the speed of an equivalently sized. Unfortunately, it's still very expensive. It turns out when you work this out, it's still quadratic scaling. No better than old school interferometry. Until some clever person comes along and looks at a paper from 1970, realizes that actually this is a Fourier transform. All you need to do is a spatial Fourier transform along the signal's measure. Turns it straight into beams on the sky. We're very good at Fourier transforms. This gets back to an old idea called the FFT telescope. There's sort of a piece of canonical radio lore that given an intensity field on the sky, emission field from the sky, the electric field on the ground is Fourier conjugate to it. Fourier transform of the field on the all angle limits, but that's just a coordinate mapping. Which means if you could just take your detectors, cover the ground in them, then all you have to do is Fourier transform it back to the sky. Surprisingly easy to do. The two things that make this almost impossible, though, are that you need a lot of these detectors. You have to tile some large 2D surface with them. Every one of them needs a big fat amplifier. And this is actually still too expensive. Computationally, this still defeats even the largest supercomputers. So we can't quite get there. It still goes quadratically with the diameter of your dish. Because there's one other trick you can pull, though, which is realize that we're on a rotating planet. We can behave like a satellite and spin. You don't need a two-dimensional surface. Take a one-dimensional. Do this trick in one dimension and let the Earth rotate and scan the sky that way. It's, again, just a more efficient way of doing things. It is much less sensitive than a full. But you can do other things. So you can build a one-dimensional telescope. People built these back in the 70s originally, probably because they were thinking about. They didn't work for lots of technical reasons back then. But if you have one of these, it's parabolic east-west, flat north-south. If I have a single detector on there, what it sees on the sky, this is the whole overhead sky, is just a narrow beam, a couple degrees wide, that runs horizon to horizon. The sky rotates, or the Earth rotates, whichever way you want to look at it, and you sweep out the northern hemisphere, since we're in the north. So then you can take a lot of detectors and put them along here, feed them into this FFT trick, and you get out a bunch of pixels. So instead of having one big fat beam, you have a bunch of independent beams. Then, because you can do this, wait for, say, a decade to get the data you need, or you can ask for more money and build 4 of them. We propose to build 4. And that essentially just takes that line of beams and splits them up east-west into more beams. And this is now something that you can actually build. This is what we call CHIME, the Canadian Hydrogen. It covers that band that we care about. It's got the resolution necessary to resolve everything we care about. Its daily survey is 30,000 square degrees that we survey the sky every day. And over the course of its survey, it's sensitive enough that we can understand the measurement. We're limited entirely by systematics. If we can control our systematics to our thermal level, we're done the measurement. There's no point repeating it. It will have been done as well as you can do it for a cosmological measurement. This is a collaboration between 3 universities in Canada, McGill in Montreal, UBC in BC, and Toronto, and the Dominion Radio Astrophysical Observatory. It's our version of NRAO. For people who aren't that familiar with Canada, this is what it looks like. Time is over here by the salmon. For people who have maps, we're over here, just south of Penticton in the Okanagan Valley. The Okanagan, by the way, is Canada's wine country. Who knew we had? Absolutely lovely, particularly after you've lived at the South Pole. Another telescope. It does not compare. We were funded for this just over 5 years ago, I guess, maybe 6 years. It made some news in Canada. This is our national newspaper, the Globe and Mail. Graphic about it. I put this up partly. It's got nice, visualization. We were going to build 5. Runs out. But my favorite part is this: that it's measured in the standard Canadian unit of area, the NHL hockey rink. So because this is an experiment, and because we wanted to make sure that it would work, and we weren't just going to, we started with a small one, what we call the Pathfinder, which was just 2 of these cylinders, just a shorter amount, where you can still do all the traditional radio interferometry to verify your project. So this we built sort of 4 years ago. It looks like this. These are oriented north-south. First lesson learned. I should say, we all came at radio astronomy from a CMB background. Everyone who's doing were physicists who did cosmic microwave background experiments. Didn't quite understand radio. So we were dabbling a little bit at first. First lesson, north is not a well-defined term. There are at least a dozen versions of north. And the north that our surveyor decided to use is off by about 1.5 degrees. For a good month, everything was transiting at the wrong time. we sorted that out. We fixed it for the big one. This is why you build prototypes. A lot of things in this design. These are 36 meters long, 20 meters. All of the processing lives over here. That kept us busy for a few years. But in the background, we were building the big one, which now is meters long, oriented and 20 meters wide for each of them. Meters are instrumented. We have detectors along the inner 80 meters by 80 meters this way, giving us our 80 meters. So for people who aren't used to looking at the sky, the whole sky, large field surveys, like I said, we're surveying every day 30,000 square degrees, roughly. 3/4 of. This is an animation of what it looks like. Just to understand where I took the celestial sphere and just unwrapped it. The dark part is night. The light part is day. The red part is what we see. Galaxy, neutron radiation, how we survey the sky. For people who prefer galactic coordinates, what it does, I find this harder to look at. It's just vague. My favorite view of this, though, is looking at it like this. This is the telescope's view, right? It stays put. Nothing on the telescope moves. That was part of the sky moves overhead. You see a little band, and things rotate through. There's the celestial. I also like this one because it's got a very evil eye sort of thing about it. I can't help it. So just to run you through the system, how am I doing? Light comes in from the sky from that little 2-degree wide band. If it comes outside that band, it does not interfere constructively on the detectors. Focus. So we only get sort of 2 degrees from the middle. It varies by frequency, but 2 degrees is the rough number. Every detector sees the same chunk of sky. There are 1,000 detectors on there. Everyone sees the exact same thing. From there, it goes through. Here's the telescope. If you stand under it and look up at one of these walkways, on the underside are all these detectors. They're just dipole antennas. They're slightly fancy dipole antennas so that they can radiation. This is what they look like in a hand. Radio pixels are easier to deal with than optical pixels. Hawaii 2. Terrifying to touch. These are break. You just fix them with a hammer. Wire them back together. Once the radiation is coupled in through the feeds into a cable, it goes through a series of analog stages, primarily an amplifier at the front. You may remember I said this was a limiting problem. We couldn't afford to build thousands and thousands of amplifiers. Historically, that was the case. If you wanted a low noise amplifier, you needed to cool it off. When I went through grad school, we had a big cryostat that got down to 40K to keep our amplifiers cold. If you want 1,000 detectors spread over a football field, it gets very expensive to have 1,000 little cryostats all cooled power and just capital cost. Well, thankfully, that's not the case anymore. Everyone wants a cell phone, and the cell phone industry has to do the same thing, but they can't keep up with extra noise or cryostats running in everyone's. So they managed to produce amplifiers that are astonishingly quiet, pennies each, require any cooling of any sort, that are thermally stabilized, that are absolute marvels of technology. Suddenly, building the low noise amplifier at the front of this is. I'll just run through this quickly. This is what our LNAs look like. Coaxial cable in. This is the size of a pack of gum. These are mass produced. You can make 1,000 of them on little circuit boards. Like I said, the amplifiers, instead of being $100,000 each, are 2 cents. Big scaling means you can afford these. It takes a lot of cable to get from these 1,000 feeds all over. We've got about 100 kilometers of coaxial cable running around. This was the cable for the small one. One is about the small one for reference is 1 clown car. There's another stage of amplification and filtering. Again, all of this sort of analog tech is now almost trivial. From there, the signals are finally digitized. They turn into bits and bytes, digital light. These custom FPGA boards out of McGill digitize all of the inputs. We've got heaps and of them to take in the 2,000 signals from the 1,000 dual polar. They also take them and they split them up into spectral windows. One nice thing about radio light is that you're measuring the raw electromagnetic field. If you want higher spectral resolution, you just run a long. Easiest thing in the world to produce a spectrum out of radio light. Every radio telescope everywhere. Arbitrary resolution. So several hundred of these run, digitize everything, channelize it. They split it up into frequencies, and then they send it on for spatial processing into the I built, which is the part that does all of that processing I mentioned earlier. Noise correlation or doing everything. This is the other piece of technology that didn't exist until recently, but it's built on GPUs. It turns out all of the math you need to do is easily written as a matrix multiplier. There are, well, billions, I think, hundreds of billions of dollars worth of industry devoted to doing matrix multiplies for a popular audience, because taking a 3D volume and projecting it onto a 2D surface, it's a projection of matrix multiply. Video games that take your little world that you're running around shooting at people in, turn them into a screen picture, that's a matrix multiply. These graphics cards that people have are matrix multiply supercomputers. Individually in credit, so this machine that has 4 GPUs in it, graphics processor, is more powerful than the world's most powerful supercomputer. And that one ran on 3 megawatts of power. This one runs on power. Again, it's astonishing the differences that consumer technology can make if you can leverage it for your. The other amazing thing that happened, you've probably heard of Moore's law, that the available computing power doubles every 18. Video cards actually have been outdoing that for the last 20 years. They've been growing faster than that. It's every, which means that by the time we actually were able to build this, we could afford to do the full old school course pairwise correlation, which was never something that was even considered and got the first round of proposals rejected because someone suggested. These things we stuff into a shipping container, hundreds and hundreds and hundreds of them, to get something on the order of a 10 petaflop machine. The point of this really is to reduce the data rate out of this, the FPGA instrument. So that dumps out about 1 terabyte of data every second. In the middle of processing, that blows up to about 1 petabyte a second. And then by the time we output it, it's down to about 1 gigabyte a second. So there's this enormous data flow going through this machine. Radio telescopes have a problem of we're trying to get from terabytes per second over several years down to a result that you could sum up in about, I don't know, bytes. So at some level, we're trying to do some huge compression problem. This is what the site looked like before we got there. It's Canada, so this is the Dominion Radio. That was before we showed up, so of course it's came and built the Pathfinder. This fence is where full charge. I said it's built now. 5 meters from the ground. Walkway, all the vectors along there. Here's a quick movie flying by. You're not allowed to fly drones around there. It's a radio quiet environment. They just broadcast like crazy. It was a maintenance day. Every now and then you have to have days when people parks are broadband. So they have shutdown days. You can see the basic structure. The digitizers live in these 2. They are the ones that record these 2,000 signals, digitize them, and then send them off at 1 terabyte a second. Live in, you might have noticed, full of graphics processing units, essentially. You may also notice the surface of these doesn't look like a very good mirror. Mesh. It's essentially because you can see it's transparent, right? We're dealing with, like I said, large, long wavelength light. Light that we have varies from 37 to 75 centimeters, which means you don't need a very smooth surface for it to focus beautifully. Working in radio has advantages like we have mesh, partly because, again, it snows here several feet a year. So these cans here contain the processors, the second stage processing. We had our first light about a year ago. This is what, for a radio astronomer, this looks beautiful. This is what Cygnus A drifting through our beam. Time runs left to right on these. This is the brightest radio galaxy in the sky goes by. See it in there. The fact that we see these wavy things, sky is moving. Everything in here looks as it should. It's been in commissioning for roughly the last year, getting all the components working properly. We have some very preliminary. This is a plot of southern horizon and northern horizon as a function. This is the sky rotating through that beam. And you can see here the galaxy going through. It goes off the bottom. A lot of it's blown out. Dynamic range problem. Big A and Cas A, the two brightest radios. Around in here, there are several. We're making I'm just going to. So the cosmology front, everything's coming along. It's on. Starting to take long chunks of data. We're integrating. We should be able to have all the data that we need to start addressing some of these questions. There's still a long path ahead analyzing it and understanding it. But in the meantime, a funny thing happened. We built a telescope that is absurdly sensitive for survey purposes. The wrong thing if you want to look at a single source. Entire sky all the time, fraction of the time, or rapidly. It's perfect. And that meant that a lot of people came knocking at our door saying, oh, I see you. Wouldn't you love to give us some of that data? Friendly said, sure, great. Where's the money? So we've had several add-ons to this. Particularly, there's a project which monitors every known pulsar in the northern hemisphere. As a project which very long baseline interferometry between CHIME and towards what we call the baseband. Most recently, and I think interesting ones, is the Fast Radio Burst project. I'll get back to that in a minute. And actually, there are, I think, now 8 or 9 sub-projects built into, all of which come through this GPU system, and every one processes that terabyte a second in a slightly different way. So there's a lot of just sending data around. But it is an amazing thing about these digital telescopes that you can take your data and process it again. Multiple, and they all run perfectly in parallel. No one ever interrupts anyone. They just all run. The downside is that suddenly we didn't have enough processing power to do all that. The upside is that these are consumer things, which lets us do, well, cosmology stuff. We can build these pulsar surveys. We can do. It is a lot of data now flowing out to these couple of real-time backends. So, like I mentioned, one of the interesting things, I'm rapidly approaching the end. Fast radio bursts are sort of the hot topic in radio astronomy. These millisecond-long blips of light that come apparently at random, predictable from unknown directions, and never repeat. One of them that does, but all the others have never repeated. In the last 10 years, we've discovered 10 of these. The characteristic thing about them is that they appear to have been broadband emission, again, that have traveled a really long way, or at least through a very long, because looking at when they arrive, so this is a plot of power as a function of frequency. The higher frequencies arrive before the lower frequencies. The lower frequency light travels more slowly through a rarefied plasma. It's static dispersion happening. You can figure out what column depth of electrons it must have passed through, and you realize fairly quickly, hang on, that can't be in our galaxy. This one, in fact, this one, not this one. One has now been localized out to a redshift of 0.2. If you work out the back of the envelope, they all must be cosmological. They're out redshifts up to maybe 3 or 4, which means they're absurdly bright, last very briefly, and no one really knows what they're from. The fact that they don't repeat makes them incredibly hard to find because you can't hope for one. There are several thousand per sky per day, but again, if you don't know exactly where to look, you have no chance. Thankfully, we're looking everywhere all the time. So we built another backend which takes all of those, what we call fan beams, these FFT beams, and searches them all. Checks on it, and this has been up and running for, we had first light a few months ago. This is what the sky looks like to them. It's a little bit different because it's not just showing the power. This is looking only for dispersed transient pulse, which is dramatically dispersed. Every one of these blips is a known radio pulsar. Pulsars are blips. This is the brightest pulsar in the northern way out and lots of side lobes for hours and hours. But this is the galaxy. So these are all. The fact that we can just every day watch the galaxy go by in pulse. No one's ever been able to. And then this summer in July, we put out an astronomer's telegram saying, OK, we found one. We just turned it on, and we're still trying to use and things, but they're coming through. So we had a commissioning event that we put up. Definitely exist in this band. And then we've had a few more. Hard to say how many, but they exist. We'll see. We'll see them. We do see them. And we're working to. So the goal here is to understand really the rate, the NDS, where they're coming from, what their origin mechanism is, what the heck is going on with these things. In parallel with this, there's this pulsar program, which has been every known pulsar in the northern hemisphere. Every day, axis, you pulsars, phase up, so shift all the phases and add them as a array onto that source and watch it go by, fold it where you know. Watch it go by. These as part of a pulsar timing array. So arrays are things that you watch arrival times of pulses. If a big gravitational wave goes by, pulses from one direction will arrive sooner than you expect, from another will be apart than you expect. This periodic sort of pulsing. We're now helping with that. But the point of it all, again, is a BAO, trying to measure the expansion history of the universe so that we can say something about what dark. We want to fill this in, and we're well on our way. I shouldn't. I've been told never put up. But here's a simulation of the sort of sensitivity we expect. These are those first 4 points. This is chime. Much higher redshift, showing the fractional error, and we can get over our systematics. We can, like I said, essentially finish this perfect world. At that level, then we'll have measured dark energy better than it. Last slide. This is my view of the observable universe. We live at the center. It runs out from us radially in every direction. Far enough, there's the CMB. Behind the CMB, there's stars, ionization. If you're looking in optical light, any light except radio, you're stuck inside this circle. If you want to look out here, you have to find something that doesn't require. That SDSS map that I put up covers this much. How much of the universe? The farthest anyone's ever done it, the high redshift one of those 4 points, is this, which goes out to redshift 1. Already, that's pretty great that we've, a macroscopic portion of the entire observable universe. CHIME covers this huge band from redshift, fully rotated around. It's a full, and of course, in my mind, I'm early in my career. This is building some telescope that you can map out all of the structure in all. So yeah, CHIME will survey the PGSA. The largest volume ever surveyed in any telescope. And we're just getting rolling now. It's exciting times. So I apologize for going long. So it depends on the scale that you're talking about exactly. On an individual galaxy, 0. Even interferometrically, with this 80 meter by 80 meter baseline, our resolution element is sort of a ½ degree. So you're looking at superclusters and larger. There, you're resolving each one at signal to noise order 1. It is like early CMB days, where people would put out these papers with a field of correlated it, and it's got this beautiful peak. Like, that's amazing. But yes, individual detections are not the point. I'm not sure I'm allowed to say, but it's no. Soon on FRB timescales. Yeah, it is. It's seen as an emission against slightly warmer than the background, but it's self-shielding the most. It's got the highest because there is still neutral gas, which hasn't yet been, but which is warm. Before that, it's actually an absorption line against the. So matter and radiation were coupled here. After they decoupled, they both cooled off in their own way. Radiation redshift. Matter cools off with the square of the. Matter cools off faster than radiation for this. When you start. There's a whole complicated story of the emission history. But we're looking for self